The universe whispers in ways we can barely comprehend, sometimes through the gentle twinkle of distant stars, sometimes through the invisible threads of gravity. Black holes. The name alone evokes mystery, awe, and maybe even a little fear. Once considered simple cosmic traps, they are now seen as laboratories for the deepest questions of physics. They challenge our understanding of space, time, matter, and perhaps even consciousness itself. He revealed that black holes, despite their reputation for swallowing everything, are not completely black. They leak radiation, small, almost imperceptible, yet relentless. This radiation, now famously known as Hawking radiation, arises from the strange dance of quantum mechanics right at the black hole's edge, the event horizon. To understand this, imagine space as a calm, empty sea. But quantum mechanics tells us this sea is never truly empty. But near a black hole, something remarkable happens. Occasionally, a particle escapes the pull of gravity, while its twin is consumed. Energy is carried away, tiny bit by tiny bit, and over eons, the black hole slowly loses mass, eventually evaporating entirely. This realization opened a Pandora's box of questions. If black holes evaporate, what happens to the information about the matter they swallowed? Quantum mechanics, our most successful theory of the microscopic world, tells us that information cannot be destroyed. The universe keeps a meticulous ledger, a record of every particle's state. This tension gave rise to one of the most profound paradoxes in modern physics, the black hole information paradox. On one hand, quantum theory says the ledger must be preserved. On the other hand, classical black hole physics suggested the ledger is destroyed. How can the universe reconcile these two truths? In 1993, a physicist named Don Page proposed a radical concept now known as the Page curve. Page suggested that the entropy of Hawking radiation, which is a measure of its information content, doesn't just rise indefinitely. Instead, it follows a subtle, counterintuitive pattern. At the beginning of a black hole's life, as it starts to radiate, the radiation appears almost completely random. Its entropy increases. But halfway through the black hole's evaporation, something changes. The radiation begins to reveal correlations, subtle patterns that encode information about what's inside the black hole. By the time the black hole fully evaporates, all the information that had fallen in is, in principle, carried back out by the radiation. The Page curve rises, reaches a peak, and then falls, a cosmic signature of information preservation. To visualize this, imagine a shredded book. At first, you only have a few random scraps of paper. That is the Page curve, a guarantee that nothing is lost forever, even in the face of the most extreme cosmic processes. But the mechanism behind this is astonishingly subtle. Enter quantum entanglement, one of the strangest and most beautiful features of the quantum world. Particles can become intertwined in such a way that the state of one can't be described independently of the other, no matter how far apart they are. The escaping Hawking radiation is entangled with the remaining black hole. Early on, this entanglement is what makes the radiation appear random, but as more radiation escapes, these correlations accumulate. Recent theoretical breakthroughs have deepened our understanding. Concepts from string theory and quantum gravity, particularly the idea of entanglement islands, show that the black hole interior isn't entirely hidden. In essence, the black hole mirrors itself, projecting the information within onto the radiation outside. The Page curve is no longer just an abstract plot. It's a concrete prediction of how information is encoded and preserved. first, it hides information, encrypts it in a way that defies our intuition, but ultimately preserves the story of every particle, every star, every event. Consider the holographic principle, a radical idea emerging from the study of black holes. It suggests that the information contained within a volume of space can be encoded on the boundary of that space, much like a hologram. Reality itself may be a projection, where the true content is written at the edges, not in the bulk. Black holes are perfect laboratories for this principle. Through Hawking radiation and the Page curve, we glimpse a universe where the distinction between inside and outside, between here and there, begins to blur. If the universe preserves information at every scale, even in the most extreme environments, then nothing is ever truly lost. Every action, every thought, every movement leaves a trace, however subtle. The cosmos is not silent. It records, remembers, and reflects. Imagine a future civilization studying a black hole billions of years from now. And yet, the story is far from complete. We have no experimental access to these fine details. We can't watch a black hole evaporate. But through theoretical physics, through thought experiments and equations, we are slowly peeling back the layers of this cosmic mystery. The Page curve is not just a graph, it is a roadmap, guiding us toward a deeper understanding of reality, information, and the very nature of existence. What we perceive as geometry, as the curvature of space and time, may emerge from the entanglement of fundamental quantum bits. Black holes, far from being destructive anomalies, become laboratories for understanding the very fabric of reality. The universe is not just matter and energy, it is information, beautifully, intricately, irreversibly encoded. The Page curve shows us that even in the deepest darkness, even in the heart of a black hole, the universe remembers, it records, it whispers, and through careful study, through curiosity and imagination, we are learning to read its language. This is more than physics. It's philosophy, it's poetry, it's a meditation on existence itself. Black holes, Hawking, radiation, entanglement, and the Page curve are not just abstract ideas. They are the universe's way of telling its story.